Point at the sky, any direction. North, south, east, west, it doesn't matter. Now tilt your head back and point straight up. That's not up in any cosmic sense. It's just the direction your planet happens to be pointing at this particular moment on this particular rotation. 8 hours from now, that direction will be somewhere completely different. 6 months from now, your planet will have swung halfway around the sun, and up will be pointing into a region of space you currently call down. The universe doesn't know you're standing up. The universe doesn't have an up. Neither, really, does the solar system. What we call up is almost entirely a story we tell ourselves about the surface of one small planet. Step back even a little to the scale of the solar system and the concept starts to dissolve. Step back further and it doesn't just dissolve. It was never really there. Tonight, we're going to follow that dissolution all the way out, past the planet, past the ecliptic, past the heliosphere, into the space where up and down stop meaning anything at all, and something stranger and more accurate takes their place. This is beyond the cosmos, slow, careful, and always headed somewhere unexpected. Subscribe if this kind of exploration is worth keeping. Take a breath. Let's go. Begin with the body you know best. The sensation of up and down, the conviction that one direction is fundamentally different from the other, is so deep in human experience that it feels like a fact about the universe rather than a fact about being a relatively large organism stuck to the surface of a planet by gravity. Gravity is what creates the whole illusion. Gravity is what makes down different from up. Gravity pulls everything toward the center of the Earth, and everything that is not in that direction becomes, by default, up. Stand anywhere on Earth and you experience gravity as a force pulling you toward the ground beneath your feet. This is true whether you are standing in Norway or in New Zealand. The person standing on the opposite side of the planet from you is also being pulled toward the ground beneath their feet, which, from your vantage point, is above your head. They are not falling. They are standing just as you are, in a gravity field that points toward Earth's center and calls that direction down. This already tells you something important. Down is not a direction in space. Down is the direction toward the nearest large mass exerting significant gravity on you. Up is away from that mass. These are local concepts rooted in the specific gravitational geometry of wherever you happen to be standing. For most of human history, this distinction did not matter. Everyone was on Earth. Gravity pointed the same way for everyone toward Earth's center, and the shared reference frame made up and down feel like absolute facts. The sky was up, the ground was down, stars were above, caves were below. The entire vertical axis of human experience was organized around a gravitational field whose source was underfoot. Even after the scientific revolution established that the Earth was a sphere and that people on the other side of the planet were somehow standing upright relative to a different down, the experience of up and down remained so immediate and so constant that it continued to feel like a fact about the universe rather than a local agreement about gravitational direction. It was not until the space age, when human beings first left Earth and found themselves floating in an environment where no gravitational direction dominated, that the full strangeness of the situation became tangible. Astronauts in orbit describe a rapid disorientation of the vertical axis, the sense that up and down are not missing but simply undetermined, that any direction could equally well be called either one, and that the body's insistence on finding a correct orientation takes days to fully quiet. This is where tonight's exploration begins, with the recognition that up and down are gravitational concepts, not spatial ones, and that the moment you leave the surface of Earth, the familiar axis starts to become unreliable. The solar system has a structure, but it is not a vertical one. To describe where things are in the solar system, astronomers use a reference plane called the ecliptic. The ecliptic is the plane of Earth's orbit around the Sun, extended outward in every direction as an imaginary flat surface that cuts through the solar system. If you were hovering far above the solar system and could see all 8 planets, they would appear to orbit the Sun in paths that lie close to this plane. The solar system looks, from a sufficiently elevated viewpoint, like a flat disk. This flatness is not a coincidence. It is a consequence of how the solar system formed. 4.5 billion years ago, the region of space now occupied by the solar system contained a vast, slowly rotating cloud of gas and dust. This cloud, like almost every large rotating cloud of material in the universe, gradually flattened as it collapsed under its own gravity. The physics of this flattening is the same physics that explains why spinning dough flattens when you toss it. Angular momentum is conserved, and as the cloud contracted, it spun faster, and as it spun faster, material in the plane of rotation spread outward, while material above and below the plane collapsed inward toward the equator. The result, after millions of years, was a flattened disk of gas and dust surrounding a central concentration that would become the Sun. Within this disk, the material clumped into rings, and within the rings, into the planets. Because all the planets formed from the same rotating disk, they all orbit in roughly the same plane. The solar system is flat because angular momentum, the tendency of rotating systems to flatten, is a fundamental feature of the way gravity and rotation interact. The ecliptic plane is, in this sense, the remnant of that original rotational axis. It is the equator of the solar system's formation process. Now here is where the concept of up and down starts to break down for the solar system. If you describe something as being above the ecliptic, you mean it is on the northern side of this imaginary plane. Below means south of the plane. But these are purely conventional labels that refer to a reference plane, not to any physical force pointing in a particular direction. Nothing falls towards the ecliptic plane. There is no gravity pulling objects to it. The ecliptic is not the solar system's floor. It is simply the reference we use to describe where things are. Moreover, the choice of which side of the ecliptic is north and which is south is itself a convention, based on looking down at the solar system from the same direction that Earth's North Pole points. Earth's North Pole points roughly toward Polaris, the North Star in the constellation Ursa Minor. By convention, the north side of the ecliptic is the side from which the planet's counterclockwise orbital motion, as seen from this direction, appears counterclockwise. This convention makes our maps consistent with terrestrial maps, but it has no deeper physical significance. There is no north built into the solar system. There is only the direction Earth happens to be tilted. The orbits of the planets are not perfectly flat, and this deviation from flatness is one of the more telling details about the actual geometry of the solar system. Earth's orbit defines the ecliptic by definition. All other planets orbit at slight angles to Earth's orbit, called orbital inclinations. Mercury has an inclination of about 7 degrees to the ecliptic. Venus is about 3.4 degrees inclined. Mars is about 1.85 degrees. The gas giants have inclinations of less than a few degrees each, with Saturn slightly more inclined than Jupiter and Uranus and Neptune close to the ecliptic. These inclinations are small, and they mean that the solar system's flat disk structure is genuinely flat, at least for the planets. The planets do not orbit in exactly the same plane as Earth, but they orbit close enough to the same plane that the ecliptic is a reasonable description of where to find them. But here is something worth sitting with carefully. These inclinations mean that every planet is sometimes north of the ecliptic and sometimes south of it. Mars, at its current orbital inclination, spends part of its year above the ecliptic and part below it. Jupiter, further out, and with a smaller inclination, still crosses the ecliptic twice per orbit. Even Saturn, slow and distant, swings above and below the reference plane over the course of its nearly 30-year journey around the Sun. And this north-south oscillation with respect to the ecliptic has no consequence for the planet whatsoever. Mars does not notice when it crosses the ecliptic plane. It does not feel different to be on the north side versus the south side. There is no physical surface there, no gravity change, no change in the particle environment or the radiation environment. The ecliptic is an imaginary plane, and crossing it is like crossing a line of latitude on Earth, a useful organizational concept that the universe itself is entirely indifferent to. The physical analogy that makes this concrete: imagine a family of balls rolling around a circular table on strings attached to the center post, like a rotating display rack in a shop. The balls roll in circles at different radii, all roughly in the plane of the table, but each at slightly different heights above the table surface. The table surface is like the ecliptic, a reference plane that organizes the description of the system, but not a surface that anything is actually attached to or falling toward. Balls above the table surface don't fall back to it. The table is a conceptual tool. The difference between the table analogy and the actual solar system is that a table is a physical surface with actual material. The ecliptic has not even that. It is purely a geometric construct, a mapping convenience, the invisible surface of which you could pass through without any instrument detecting it. Why, then, do we talk about the solar system as having a plane? Because the planets do genuinely cluster near the ecliptic. Their orbits are not randomly distributed over all possible directions. They are confined within a few degrees of this reference plane. That clustering is real. But the reason for the clustering is history, the angular momentum of the protoplanetary disk, not any ongoing physical force that keeps the planets pinned to the ecliptic. Some objects in the solar system are not confined to the ecliptic, and studying their orbits reveals something important about the full three-dimensional shape of the solar system. Comets are the most dramatic example. Long-period comets, those with orbital periods of hundreds or thousands or even millions of years, do not preferentially orbit near the ecliptic. They arrive from all directions, with orbital inclinations spanning the full range from 0 to 180 degrees. Some long-period comets orbit in the same direction as the planets, what astronomers call prograde orbits. Others orbit in the opposite direction, retrograde. Some are highly inclined, sweeping over the poles of the solar system on trajectories that carry them far north and south of the ecliptic before swinging back in toward the Sun. This isotropic distribution of long-period comet orbits was one of the key pieces of evidence that led Jan Oort, in 1950, to propose the existence of the Oort Cloud. If long-period comets came from a disc-shaped reservoir like the Kuiper Belt, they would arrive preferentially from directions near the ecliptic. The fact that they arrive from all directions suggests they come from a roughly spherical reservoir surrounding the solar system, what we now call the Oort Cloud. The Oort Cloud is estimated to extend from roughly 2,000 to 100,000 astronomical units from the Sun in a roughly spherical distribution. Objects in the Oort Cloud are not in the ecliptic plane. They orbit at all inclinations above and below, east and west, at every angle relative to the ecliptic. The Oort Cloud is the solar system in its full three-dimensional extent, unconstrained by the flat disk structure of the planetary zone. Asteroids provide a middle ground. Most asteroids orbit in the main asteroid belt between Mars and Jupiter, with inclinations typically less than about 20 to 30 degrees to the ecliptic. But there are exceptions. Some asteroids orbit at high inclinations, carrying them far above and below the ecliptic on each orbit. The asteroid Pallas, one of the largest in the main belt, has an inclination of about 34 degrees, meaning it swings significantly north and south of the ecliptic plane. Some near-Earth asteroids have even higher inclinations, crossing the ecliptic at steep angles. Dwarf planets and Kuiper belt objects similarly span a range of inclinations. Pluto's orbit is inclined about 17 degrees to the ecliptic. The dwarf planet Eris has an inclination of about 44 degrees, meaning it spends much of its orbit quite far from the ecliptic plane. Makemake and Haumea also have significant inclinations. The scattered disk population, gravitationally stirred up by interactions with Neptune, shows a wide range of inclinations. All of this tells us that the flat disk of the planetary system is a feature of the most massive, most dynamically organized part of the solar system, where the conservation of angular momentum from the original disk has maintained a preference for near-ecliptic orbits. But the solar system as a whole, including its most distant and most dynamically disturbed members, occupies three-dimensional space with no strong preference for any particular vertical direction. The concept of north of the ecliptic versus south of the ecliptic is in some ways useful for describing where things are in the solar system, but it conceals a deeper question. Is there anything physically special about one of those directions compared to the other? The answer, for the solar system in isolation, is no. The Sun's gravity is symmetric around any plane through the Sun. A satellite orbit that is exactly symmetric about the ecliptic, spending equal time above and below, would experience the exact same gravitational environment as one that is always in the ecliptic. There is no special physics at the ecliptic. There is no force pointing perpendicular to the ecliptic that either attracts things toward it or repels them from it. The ecliptic is, physically, a ghost. But the solar system is not entirely isolated. It exists within a galaxy, and the galaxy's structure does impose a physical preference for certain directions. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across and roughly 1,000 light-years thick at our location in one of the spiral arms. The galactic plane, the disk of the Milky Way, has its own gravitational effect on objects in the solar system. The disk of the galaxy creates a tidal force on the Oort cloud, gently nudging the orbits of distant cometary bodies. This galactic tidal force acts perpendicular to the galactic plane, and its effect is to preferentially perturb Oort cloud objects in orbits perpendicular to the galactic plane, sending them inward toward the Sun more efficiently than objects orbiting parallel to the galactic disk. This galactic tidal effect is real and has been invoked to explain why long-period comets arrive preferentially from certain galactic latitudes rather than uniformly from all directions. The galactic plane is, in this sense, a physically meaningful reference, not for the solar system's internal dynamics, but for its interaction with the galaxy around it. The solar system's ecliptic plane and the galactic plane are not aligned. The galactic plane of the Milky Way is tilted at about 60 degrees relative to the ecliptic. This means that if you pointed straight up from the north ecliptic pole, you would not be pointing toward the galactic North Pole. These are two different reference frames, two different senses in which one might talk about up or down or north and south in our region of the universe, and they are tilted substantially relative to each other. For objects in the outer solar system, both reference frames matter somewhat. Objects close to the galactic plane feel a stronger tidal effect from the galactic disk. Objects at high galactic latitude are in the part of the Oort cloud that is least efficiently perturbed by galactic tides. The full picture of the solar system's three-dimensional structure involves both the ecliptic plane, which describes the flat inner disk, and the galactic plane, which describes the external environment that shapes the outer regions. The fact that the ecliptic and galactic planes are not aligned also reveals something about the history of the solar system's orientation within the galaxy. The Sun orbits the galactic center at a speed of roughly 230 kilometers per second, taking approximately 225 to 250 million years to complete one full orbit of the galaxy. This orbital period is sometimes called the galactic year or cosmic year. The Earth has experienced roughly 20 of these galactic years in its lifetime. As the Sun moves through the galaxy on this slow orbit, it also oscillates vertically, bobbing above and below the galactic plane with a period of roughly 30 to 35 million years. Currently, the solar system is slightly north of the galactic plane and moving northward, having crossed the plane roughly 3 million years ago. In about 15 million years, it will reach its maximum displacement north of the plane and then begin swinging back south. This oscillation means that what astronomers mean by above the galactic plane changes over tens of millions of years of solar system history. The solar system is not fixed in its galactic latitude. It moves through the galactic disk over time, periodically moving through denser regions of the disk where star-forming molecular clouds are more numerous, and periodically emerging into the relatively sparse region above or below the plane. The ecliptic's tilt relative to the galactic plane is not fixed either, at least not on astronomical timescales. The precession of Earth's rotation axis, which drives the cycle of astronomical precession that changes the direction of Earth's North Pole over 26,000 years, does not directly change the orientation of the ecliptic. But the slow evolution of the solar system's orbit in the galaxy and the gravitational perturbations of passing stars and molecular clouds on the outer solar system could over very long timescales alter the orientations of planetary orbits. The practical point is this: there is no cosmic north that has remained constant throughout the solar system's history. The direction we call north in ecliptic coordinates is determined by Earth's current orbital orientation and its current axial tilt. In the distant past, these were different. In the distant future, they will be different again. North of the ecliptic is not an eternal address, but a snapshot description that is valid now and becomes increasingly approximate as you look further backward or forward in time. There is a specific feature of the solar system's orientation that generates genuine scientific discussion and that makes the question of up in the solar system more interesting than it might initially seem: the mysterious tilt of the Sun. The Sun, like all stars, rotates. It does not rotate as a rigid body because it is made of plasma, and different latitudes rotate at different speeds, a phenomenon called differential rotation. The equatorial regions of the Sun rotate faster than the polar regions, with the equatorial region completing one rotation in about 24.5 days, while the polar regions take closer to 35 days. The orientation of the Sun's rotational axis, its solar North Pole, defines the Sun's own equatorial plane. One would expect the planets, having formed from the same disk of material that rotated around the young Sun, to orbit in a plane close to the Sun's equatorial plane. But they don't. Quite. The ecliptic is tilted about 7 degrees relative to the Sun's equatorial plane. This small but real tilt between the solar equatorial plane and the planetary orbital plane is called the solar obliquity, or the invariable plane offset. It is thought to result from several possible mechanisms. One proposal is that an early interaction with a passing star slightly deflected the outer solar system's orientation after the planets had formed. Another is that the Sun itself has migrated somewhat relative to the original disk orientation over 4.5 billion years of stellar evolution. A third involves the gravitational influence of the planets over long timescales slowly precessing the Sun's rotation axis. The invariable plane is a useful concept here. Rather than using the ecliptic, which is specific to Earth's orbit, planetary scientists sometimes use the invariable plane, which is the plane perpendicular to the total angular momentum vector of the solar system. Because the angular momentum of all the planets added up is dominated by Jupiter and Saturn, the invariable plane is close to the orbital planes of those two giants. the invariable plane is tilted about 1.5 degrees from the ecliptic. Neither the ecliptic nor the Sun's equatorial plane nor the invariable plane defines a physical flaw of the solar system. They are all reference planes, each useful for specific purposes. The ecliptic for comparing Earth relative positions, the invariable plane for the solar system's overall angular momentum structure, the Sun's equatorial plane for solar physics. Each is tilted slightly with respect to the others, and none of them is more real than the others as a physical surface. This multiplicity of reference planes is not a problem or a confusion. It is a reflection of the genuine complexity of describing direction in a system that does not have a built-in vertical axis. Leave the planetary plane entirely now and consider what it would actually feel like, physically, to travel up out of the solar system, perpendicular to the ecliptic, away from the flat disk of the planets, into the space above or below the solar system's familiar architecture. The first thing to understand is that nothing physically special happens as you cross the ecliptic plane on your way out. You are not passing through any surface. There is no change in the density of the interplanetary medium, no change in the solar wind, no change in the radiation environment, no change in the gravitational field structure. The ecliptic is not a membrane. A spacecraft or a hypothetical traveler crossing the ecliptic does not register the crossing in any way that instruments would detect. Compare this to what happens when you cross the boundary of the heliosphere, the heliopause. As discussed in our previous exploration of the solar system's edge, the heliopause is a real physical boundary where the solar wind's pressure equals the pressure of the interstellar medium. Crossing it changes the particle environment in ways that instruments can directly measure. Voyager 1 crossed the heliopause in 2012 and immediately registered a change in the plasma environment. The heliopause is not a drawn line. It is a real physical transition. The ecliptic is nothing like this. It has no physical reality beyond the fact that the planet's orbits cluster near it. As you move away from the ecliptic plane, above or below in the conventional direction, the immediate environment changes only in the sense that you are moving away from the planets. The density of other objects in the solar system decreases. The probability of encountering an asteroid, a comet, a Kuiper belt object gradually diminishes as you move above or below the disk. The solar system is not empty perpendicular to the ecliptic, but it is considerably less populated there than within the disk. At large distances above or below the ecliptic, you would find yourself in a region of the heliosphere where the solar wind still flows outward from the Sun, but where the density of small bodies is lower than in the disk. You would not be in a qualitatively different part of the solar system. You would simply be in a quieter region of it. The analogy that makes this concrete: imagine the solar system as a frisbee with a lump in the middle. The frisbee is the disk of the planets and the debris disk beyond Neptune. The lump in the middle is the Sun. Travel across the surface of the frisbee and you are in the planetary disk. Travel above or below the frisbee and you are in the polar regions of the heliosphere, where the solar wind flows outward into space just as it does at other latitudes, but where the flat disk of debris is no longer around you. Moving perpendicular to the ecliptic, then, is just moving to a less populated part of the same system. The direction has no special physical status. The description above the ecliptic is precisely as meaningful as saying south of the Mississippi River for describing a location on Earth's surface, a useful geographic reference, but not a description of anything special about the physics of that location. There is a particular case where the solar system's geometry involves a real and surprising distinction between above and below, the magnetic field of the Sun. This distinction does not involve a vertical axis in the gravitational sense, but it is worth exploring because it shows that even in the absence of gravitational up and down, the solar system has genuine structural asymmetries. The Sun's magnetic field is generated by the circulation of electrically conducting plasma in its interior. The resulting magnetic field has a complex structure near the surface, with regions of intense local field called active regions, sunspots, and associated phenomena. But at large distances from the Sun, the magnetic field simplifies. Far from the surface, the Sun's magnetic field looks approximately like a dipole, a north-south bar magnet configuration, with one magnetic pole near the Sun's north geographic pole and one near the south geographic pole. The solar wind carries the Sun's magnetic field outward into the heliosphere. As the Sun rotates, the outward flowing field lines are wrapped into a spiral, like water from a rotating sprinkler. This spiral structure, called the Parker spiral after the physicist Eugene Parker, who first described it, is the dominant magnetic structure of the inner heliosphere. The critical point for our discussion is the heliospheric current sheet. This is a surface extending outward from the Sun's magnetic equator, where the polarity of the magnetic field changes from pointing outward, away from the Sun, to pointing inward, toward the Sun. It is a wavy, undulating surface that rotates with the Sun, creating a pattern sometimes compared to the shape of a spinning ballerina's skirt. The heliospheric current sheet is not flat. It wobbles above and below the equatorial plane as the Sun rotates. Crossing the heliospheric current sheet has real physical consequences. The change in magnetic field polarity across the sheet affects the flow of charged particles, including cosmic rays from outside the solar system. The cosmic ray flux is slightly higher on one side of the sheet than the other in certain energy ranges, due to the way the sheet's magnetic structure deflects and channels particles. Spacecraft crossing the heliospheric current sheet register measurable changes in the magnetic field direction and in the particle environment. Here is a genuine physical distinction between sides of a surface in the solar system. But notice what this distinction is and is not. It is a distinction between two sides of the heliospheric current sheet, not between above and below in any vertical sense. The heliospheric current sheet is not horizontal. It wobbles around the solar equatorial plane, sometimes extending north of the ecliptic and sometimes south, depending on the sector and the phase of the solar cycle. The physically meaningful distinction here is between the two magnetic polarities, not between any fixed up and down direction. This is characteristic of the solar system's real structure. The physically meaningful distinctions are between different magnetic sectors, different gravitational potential contours, different regions of particle density, all of which are structures that can be inclined at any angle to the ecliptic and that bear no particular relationship to what we would intuitively call vertical. The question of what up means becomes most acute when you consider the navigation of spacecraft in the solar system, because spacecraft navigation requires precise coordinate systems, and choosing those coordinate systems involves real decisions about what reference frames to use. NASA and the other space agencies use several different coordinate systems depending on the application. The most commonly used for describing positions in the solar system is the ecliptic coordinate system, in which the ecliptic defines the reference plane and the coordinate system uses the direction of the vernal equinox, the point where the Sun crosses the ecliptic moving northward at the spring equinox, as the reference direction within the plane. This is the coordinate system in which you might say that a spacecraft is 2 astronomical units from the Sun, at 15 degrees north ecliptic latitude. For describing positions in the sky as seen from Earth, the equatorial coordinate system is more common. This uses Earth's equatorial plane as the reference plane and again uses the vernal equinox direction as the reference direction in the plane. In equatorial coordinates, positions are given in right ascension and declination, the celestial equivalents of longitude and latitude. Neither the ecliptic coordinate system nor the equatorial coordinate system is the way the solar system is actually oriented. They are both human-chosen reference frames designed to make certain calculations easy or to make certain descriptions intuitive. Spacecraft navigators use whichever coordinate system is most convenient for the task at hand, and they routinely convert between systems as needed. For mission planning, particularly for missions that leave the plane of the ecliptic, a different consideration comes into play. The inclination of the spacecraft's orbit to the ecliptic tells you something practical about what the spacecraft will encounter. A spacecraft in the ecliptic plane passes through the densest part of the asteroid belt. A spacecraft with a high inclination orbit will spend time above and below the ecliptic, where the density of small bodies is lower. This practical distinction influences mission design, but it does not imply that above the ecliptic is physically different from in the ecliptic in any fundamental sense. The only spacecraft that have deliberately traveled significantly out of the ecliptic plane for scientific purposes are the Ulysses mission, launched in 1990, and the out-of-ecliptic portions of the Voyager trajectories. Ulysses was specifically designed to study the Sun from a high-inclination orbit, eventually swinging over the solar poles. To achieve this orbit, which required leaving the ecliptic plane almost entirely, Ulysses used a gravitational assist from Jupiter, which flung it into an orbit tilted about 80 degrees from the ecliptic. From this high-inclination vantage point, Ulysses studied the solar wind and the heliosphere from latitudes not accessible from the ecliptic plane. It made the first direct measurements of the solar wind at high heliographic latitudes, finding that the fast solar wind that had been predicted to come from the polar regions of the Sun was indeed present at high latitudes, with properties somewhat different from the slower, denser solar wind measured by spacecraft in the ecliptic. The Ulysses findings reinforced something important. The heliosphere is genuinely three-dimensional. The solar wind flows in all directions, not just in the ecliptic. The Sun's influence extends above and below the disk of the planets with similar vigor. The solar system is not fundamentally two-dimensional in any physical sense. The flat disk of the planets is a dynamical feature arising from the conservation of angular momentum in the formation process. The underlying physics is fully three-dimensional. There is a thought experiment that clarifies the arbitrariness of up in the solar system so viscerally that it is worth working through carefully. Imagine you are floating in space, far from any planet, roughly 10 astronomical units from the Sun. The Sun is a bright but small disk in your field of view, not the commanding presence it is from Earth's surface, but still by far the brightest object in the sky. The planets, most of them too far or too small to see without a telescope, are irrelevant for the moment. You are simply floating in interplanetary space in the outer solar system. Now I ask you, which way is up? In one meaningful sense, you might say up is away from the Sun. The Sun is the solar system's center of gravity, and so down in a very broad sense is toward the Sun, just as down on Earth means toward Earth's center. If you define the solar system's down as toward the greatest source of gravity, then up is away from the Sun. But this gives you a radial direction, not a vertical one. Up, in this sense, is not a single direction. It is every direction that points away from the Sun simultaneously, a sphere of directions rather than a single axis. From where you are hovering, up in this gravitational sense is every direction except toward the Sun. That is not particularly useful as a navigation concept, and it doesn't match what we mean by up in ordinary language. Alternatively, you might try to use the ecliptic as a reference. Up could mean north of the ecliptic, the direction that the ecliptic's normal vector points toward in the conventional astronomical definition. This gives you a specific direction in space, the direction of the ecliptic North Pole. But as we have established, this direction has no physical significance. Nothing is above the ecliptic in any physical sense. This is merely a coordinate direction imposed by human convention. A third option would be to use the galactic plane as a reference. North of the galactic plane, the direction the Milky Way's North Pole points, is a physically somewhat more meaningful direction because the galactic disk does have gravitational structure. But even this is not up in any absolute sense. It is a direction relative to a particular large structure that we happen to inhabit. The thought experiment reveals the problem. There is no unambiguous up in the solar system because there is no single dominant source of vertical gravity. On Earth's surface, the gravitational field of Earth provides an unambiguous down. In the solar system, the Sun's gravity is radial, pointing toward the Sun from every direction, and the ecliptic is a reference plane rather than a gravitational equator. There is no single direction that is unambiguously perpendicular to a dominant gravitational force in the way that the vertical is unambiguous on Earth. What there are, instead, are several useful reference directions and planes, each one useful for certain purposes and none more physically fundamental than the others. The solar system is genuinely three-dimensional, and describing positions and orientations within it requires multiple reference frames rather than a single intuitive axis. The question of how planetary orbits are actually oriented in 3 dimensions connects to one of the most interesting discoveries about exoplanetary systems, which is that the flat disk architecture of our solar system is not universal among planetary systems in the galaxy. When astronomers discovered the first exoplanets in the 1990s using the radial velocity technique, which detects the subtle back and forth motion of a star caused by the gravitational tug of an orbiting planet, they could measure the planet's orbital period and the minimum mass, but not the orbital inclination with respect to the sky plane. When the transit method came into wide use with missions like Kepler, which detected the tiny dimming of a star's light as a planet passed in front of it, astronomers gained access to planets whose orbital planes happen to be nearly edge-on to us. But the transit method is inherently biased toward finding planets in edge-on orbits. What has emerged from 2 decades of exoplanet discovery is a picture of remarkable diversity in planetary system architectures. Some systems have all their planets orbiting in nearly the same plane, like our solar system. Others show substantial mutual inclinations between planets, with inner and outer planets orbiting at significant angles to each other. Some systems have planets in highly inclined orbits, even retrograde orbits, circling their host stars in the direction opposite to the star's rotation. The discovery of retrograde hot Jupiters, giant planets orbiting very close to their host stars in the direction opposite to the star's rotation, was one of the more surprising findings of early exoplanet science. In our solar system, all 8 planets orbit the Sun in the same direction as the Sun rotates, prograde, a natural consequence of forming from the same rotating disk. A retrograde planet cannot have formed from such a disk. It must have been perturbed into its current orbit by some later dynamical process, such as gravitational interactions with other planets or the influence of a distant stellar companion. These misaligned and retrograde systems tell us that the flat disk, coplanar, co-rotating architecture of our solar system is not the only way a planetary system can be organized. It may not even be the most common way, though the discovery biases of various detection methods make it difficult to determine the true distribution of orbital architectures in the galaxy. The important implication for our question about up in the solar system. Even the mild version of up as north of the ecliptic, perpendicular to the planet disk, is a concept that has different meanings in different planetary systems. For a retrograde hot Jupiter, the star's rotation axis and the planet's orbital angular momentum vector point in opposite directions. The ecliptic equivalent for such a system would be perpendicular to something that is itself already perpendicular to everything else. The concept of above the disk or above the ecliptic in a system with such extreme misalignments is almost entirely devoid of meaning. The relationship between the ecliptic plane and the orientation of the Moon's orbit introduces another layer of complexity to the question of vertical direction in the Earth-Moon system specifically. The Moon orbits Earth in an orbit tilted about 5.1 degrees to the ecliptic. This tilt, while small, has important consequences. It means the Moon does not pass in front of the Sun every month, which would otherwise produce a solar eclipse on every new moon. It also means the Moon does not enter Earth's shadow every month, which would produce a lunar eclipse on every full moon. Eclipses only occur when the Moon is near the line of intersection of its orbit with the ecliptic, called the line of nodes. When both conditions are met, a new or full moon near a node, an eclipse becomes possible. The orientation of the Moon's orbital plane relative to the ecliptic changes over time. The line of nodes precesses, rotating slowly in space with a period of about 18.6 years. This nodal precession means that the Moon's orbit, already tilted relative to the ecliptic, is also slowly rotating, so that the direction you need to point to be perpendicular to the Moon's orbital plane changes over an 18.6-year cycle. Add to this the fact that Earth's own equatorial plane is tilted 23.4 degrees to the ecliptic, a tilt called the obliquity of the ecliptic, and you have a situation in which three distinct reference planes, Earth's equatorial plane, the ecliptic, and the Moon's orbital plane, are all at different angles to each other, all slowly changing their relative orientations over different timescales. For an astronaut on the Moon, the question of up is temporarily resolved by the Moon's own gravity. Down is toward the Moon's center, up is away from it. But the direction that down points in the larger context of the solar system changes over the Moon's orbit. At one point in the orbit, the Moon's surface gravity points one way. 2 weeks later, it points in a very different direction relative to the Sun, the ecliptic, the galaxy. The Moon's surface is one of the few extraterrestrial locations where a human being has stood and directly experienced the concept of up and down. The 12 astronauts who walked on the lunar surface during Apollo missions experienced lunar gravity, about 1/6 of Earth's, pulling them toward the lunar surface with enough force to make down feel unambiguous. But even that experience came with the visual knowledge, visible in every panoramic photograph from the Moon, that Earth was somewhere in the lunar sky, sometimes overhead and sometimes on the horizon depending on the landing site's latitude, and that the black space extended in all directions beyond a horizon far closer than Earth's due to the Moon's small size. The Apollo astronauts were the first human beings to directly experience the arbitrariness of up in a practical existential sense. Floating in the command module on the way to the Moon, the concept of up was negotiated rather than given, a matter of the spacecraft's orientation and the crew's preference rather than a gravitational fact. Looking out the window at Earth growing smaller against the stars, up could be defined by whichever window you happened to be looking through. There is a specific and beautiful measurement that illustrates the question of orientation in the solar system in a way that numbers can barely capture. The direction the solar system is moving through the galaxy and what that implies about the orientation of the solar system relative to its own trajectory. The solar system orbits the galactic center at about 230 kilometers per second. This is a velocity more than 600 times faster than a rifle bullet, or about 0.08% of the speed of light. The direction of this orbital motion, which points roughly toward the constellation Cygnus in the sky, defines a kind of forward direction for the solar system in its galactic journey. Now, consider the ecliptic plane relative to this direction of motion. The ecliptic is the reference plane of the planets, inherited from the angular momentum of the protoplanetary disk. The galactic direction of motion is determined by the solar system's orbital trajectory around the galactic center. There is no particular reason why these two should be aligned, and in fact, they are not. The ecliptic plane is tilted about 60 degrees relative to the galactic plane. The direction of the solar system's galactic motion is roughly in the galactic plane, so the flat disk of the solar system is not oriented face-on to the direction of travel through the galaxy, like a coin rolling on a table. It is tilted at a substantial angle, like a spinning top that has partially fallen over. This orientation is not meaningless. It affects how the solar system's outer regions interact with the interstellar medium through which the Sun is moving. The heliosphere is compressed in the direction of the Sun's motion through the interstellar medium and extended in the trailing direction. The heliopause is closer in the upwind direction, where the Sun is moving toward the incoming interstellar material, and more distant in the downwind direction. The Sun's movement through the interstellar medium also creates a bow shock, a region of compressed interstellar material ahead of the heliosphere. Though, whether the Sun currently creates a true bow shock in the technical sense has been debated since Voyager's measurements showed the interstellar flow speed is lower than some estimates had assumed. The question of whether there is a bow shock ahead of the solar system in the direction of galactic motion is genuinely uncertain. In any case, the solar system has a direction of travel through the galaxy, and that direction is not aligned with anything we would call up in a conventional terrestrial sense. The solar system is hurtling sideways relative to the ecliptic through the interstellar medium at 230 kilometers per second, sweeping through the galaxy with the planet's disk tilted at a substantial angle to the direction of travel. The axial tilt of Earth, 23.4 degrees relative to the ecliptic, generates a question that is worth addressing directly because it touches on the relationship between the solar system's structure and our everyday experience of up, down, and direction. Earth's axial tilt means that Earth's north pole does not point perpendicular to the ecliptic. It points at a direction roughly 23.4 degrees away from the ecliptic north pole. Over the course of a year, as Earth orbits the Sun, the direction Earth's north pole points in space remains roughly constant, always pointing toward Polaris, with some slow variation due to precession. This constant orientation while the planet moves through its orbit is what causes the seasons. This means that the direction you would point if you wanted to point toward the top of Earth, toward the North Pole, is not the same as the direction you would point to indicate north of the solar system's ecliptic plane. The two directions are separated by 23.4 degrees. Polaris, the current North Star, is very close to the direction of Earth's rotation axis extended into space, the North Celestial Pole. This makes Polaris useful for navigation because it appears nearly stationary in the northern sky as Earth rotates. But Polaris is not at the ecliptic North Pole. The ecliptic North Pole is in a different part of the sky, in the constellation Draco, not near Polaris. This is subtle but important. When you look at Polaris, you are not looking perpendicular to the solar system's disk. You are looking along Earth's rotation axis, which is tilted to the ecliptic by the 23.4 degree obliquity of the ecliptic. The north that you navigate by, the direction of Polaris, is not the same as the north of the solar system's reference plane. Moreover, Polaris will not always be the North Star. Due to the precession of Earth's rotation axis, which traces a cone around the ecliptic North Pole with a period of 26,000 years, the direction of Earth's North Pole slowly changes, pointing at different stars over millennia. About 5,000 years ago, the North Star was Thuban in the constellation Draco, which the ancient Egyptians may have used in aligning the Great Pyramid. In about 12,000 years, the North Star will be Vega in the constellation Lyra. The precession means that even the concept of north as defined by Earth's rotation axis is not stable over long periods. The axis traces a slow circle in the sky, cycling through different north stars over the 26,000-year precession period. The only stable north for the solar system is the ecliptic north pole, defined by the invariable planes perpendicular, and that direction is not marked by any bright star. This is another layer of the dissolution of up. Even within the Earth-Sun system, at a level that predates any considerations of the broader galaxy, the concept of vertical direction is complicated by Earth's tilt, by precession, by the distinction between the equatorial and ecliptic poles, and by the fact that what serves as our North Star changes over thousands of years. Let's now think carefully about gravity in a more general way, because the question of up and down in the solar system is ultimately a question about gravity, and gravity's behavior in the solar system is more interesting than the simple picture of the sun pulling everything toward its center. Gravity in the solar system is not just the sun pulling the planets. Each planet pulls on all the other planets. The sun pulls on every body in the system. The planets pull on the sun. The moons pull on their parent planets and on each other and on other bodies nearby. Smaller bodies, asteroids and comets and dust grains pull on everything and are pulled by everything. The gravitational field of the solar system is a complex superposition of all these individual contributions. In this complex gravitational field, there are interesting structures called gravitational potential contours, surfaces of equal gravitational potential energy. These surfaces are not flat. Near the Sun, they are roughly spherical. Farther out, they are distorted by the presence of the planets. Jupiter, being far more massive than the other planets, causes the largest distortion. The gravitational landscape near Jupiter is significantly different from the gravitational landscape of the rest of the solar system. Within this complex field, there are points of particular interest called Lagrange points. These are the 5 locations in the two-body gravitational problem of a large body and a small body, such as the Sun and Jupiter, or the Earth and the Moon, where the gravitational forces and the centrifugal force due to the system's rotation exactly balance, creating points of local equilibrium where a small object can remain stationary relative to both large bodies. The Lagrange points L4 and L5, trailing and leading the planet at 60 degrees in its orbit, are stable, meaning objects placed near them tend to remain there even if slightly perturbed. Jupiter's L4 and L5 points host the Trojan asteroids, 2 clouds of bodies that share Jupiter's orbit but stay roughly 60 degrees ahead and behind in the orbit. Earth's L4 and L5 have a much smaller population but are not empty. These Lagrange points are not special because of any vertical direction. They are special because of the balance of forces in the orbital plane, essentially horizontal features of the gravitational landscape. But they illustrate that the solar system's gravity field has structure beyond the simple radial pull of the Sun, structure that exists in the plane of the orbits and that creates preferred locations for material to accumulate. The question of up in the solar system's gravitational field is tangled precisely because the gravitational potential does not define a preferred vertical direction in the way that Earth's gravity does. On Earth, the gravitational potential decreases monotonically with height above the surface, and this monotonic decrease is what defines down as the direction of decreasing potential. In the solar system, the gravitational potential has a much more complex structure with local minima near each planet, saddle points at Lagrange locations, and an overall decrease in the Sun's gravitational influence with distance. There is no single direction that plays the role of down for the solar system as a whole. The Voyager probes provide perhaps the most compelling experiential illustration of the dissolution of up in the solar system. because their trajectories took them from the tight two-dimensional world of the ecliptic through regions where the concept of solar system orientation becomes increasingly abstract. Voyager 1 launched in 1977 and encountered Jupiter in 1979 and Saturn in 1980. Its trajectory through the Saturn system, specifically its close flyby of Saturn's moon Titan, deflected the spacecraft onto a path that carried it upward relative to the ecliptic, away from the plane of the planets, and outward into the heliosphere at an angle of about 35 degrees above the ecliptic. This trajectory was chosen not because above the ecliptic was a scientifically interesting place, but because the close Titan flyby that scientists had prioritized for its scientific value happened to deflect the spacecraft in that direction. The choice between exploring Titan up close versus continuing toward Uranus and Neptune was made in favor of Titan, and the 35-degree inclination above the ecliptic was the geometrical consequence. After the Saturn encounter, Voyager 1 was no longer in the plane of the planets. It was climbing upward relative to the ecliptic, moving away from the Sun and simultaneously drifting away from the flat disk of the solar system. From this vantage point, as Voyager 1 looked back at the solar system from a position above the ecliptic, the view would have been, theoretically, that of a slight elevation above the disk, the planets spread out below in their flat orbits. I say theoretically because Voyager 1's cameras were shut down after the pale blue dot images in 1990 to conserve power. The cameras could not, in the end, give us the view that we might have hoped for. But the famous family portrait images, taken from a distance of about 6 billion kilometers in 1990, do include images from a vantage point somewhat above the ecliptic plane, and the positions of the planets in those images, scattered across a range of ecliptic latitudes rather than all lying in a single line, reflect Voyager 1's elevated position above the disk. Voyager 2 took a different trajectory that kept it closer to the ecliptic, allowing it to continue to Uranus and Neptune. Voyager 2 is currently about 20 degrees below the ecliptic plane, heading in the roughly southward direction in ecliptic coordinates. The two Voyager probes are thus heading in different directions out of the solar system, one roughly above the ecliptic plane and one roughly below it. And the physical experience of both probes, as measured by their instruments, shows no difference that could be attributed to their position above or below the ecliptic. The interstellar medium they are now traveling through is not different on one side of the ecliptic versus the other. The cosmic ray flux is similar. The local plasma density is similar. The direction above or below the ecliptic, as a physical distinction, has simply evaporated as an irrelevancy once you leave the solar system's disk. The stars closest to the solar system provide a context for thinking about orientation in interstellar space, and they reveal that even the concept of above the ecliptic has no meaning beyond the immediate vicinity of the Sun. Alpha Centauri, at 4.37 light-years, is the nearest star system. It is a binary system with a third component, Proxima Centauri, which is actually the closest individual star at 4.24 light-years. From the perspective of the solar system, Alpha Centauri is currently in the southern sky, well below the celestial equator. To travel toward Alpha Centauri from the solar system, you would head south in ecliptic terms, well below the ecliptic plane. But this has nothing to do with any physical meaning of south. It is simply where Alpha Centauri happens to be in the sky right now, from Earth's current vantage point. In 26,000 years, Earth's precession will have changed the orientation of the celestial equator, though not the ecliptic, and Alpha Centauri will be in a somewhat different position relative to the celestial coordinates. In hundreds of thousands of years, the proper motion of Alpha Centauri through the galaxy will have changed its apparent position more substantially. Conversely, Epsilon Eridani, one of the nearest stars with confirmed evidence of a planetary system, lies to the north of the celestial equator. To travel from the solar system toward Epsilon Eridani would be to head northward in ecliptic terms. There is nothing more or less important about this direction than the southward direction toward Alpha Centauri. Both are just directions in space, pointing toward different stars at different distances. The nearest star to the solar system in the north ecliptic pole direction, the direction that would be most directly up from the solar system if up meant ecliptic north, is not Alpha Centauri. It is not a well-known star, because the ecliptic North Pole direction happens not to be pointing toward any particularly famous or nearby star. The ecliptic North Pole is in the constellation Draco, and the nearest stars in that general direction are not the nearest stars overall. Alpha Centauri happens to be almost directly in the south ecliptic direction because of the solar system's current orientation, not because of anything physically special about the south ecliptic direction. The stars are distributed through three-dimensional space in all directions from the Sun, with no preference for any particular direction relative to the ecliptic. The ecliptic North Pole direction, the conventional up of the solar system, is not more populated with stars than any other direction. It is not the direction toward the galactic center, which is in Sagittarius and roughly in the galactic plane. It is not the direction of any particular structure in the galaxy. The concept of above the ecliptic or below the ecliptic, already physically meaningless within the solar system, is completely meaningless in the context of the galaxy. The galaxy does not know about the ecliptic. The ecliptic is a parochial concept rooted in the specific orbital plane of one star's third planet in one solar system among 400 billion. Now, let's consider what all of this means for how we experience the universe, not just abstractly, but in terms of the actual spatial and perceptual disorientation that awaits human beings who travel beyond Earth. The vestibular system, the inner ear's balance mechanism, depends on gravity to function as an up-down detector. The tiny calcium carbonate crystals called otoliths that are part of the vestibular apparatus settle toward the bottom of their fluid-filled chambers under gravity, and the pattern of nerve signals this creates tells the brain which way is down. In microgravity, the otoliths do not settle. They float, and the signals they send to the brain are confused. This is a major contributor to space motion sickness, the disorientation and nausea that a significant fraction of astronauts experience in the first days of weightlessness. After a few days, the brain adapts. It learns to use other cues, the position of the body in the spacecraft, the visual reference of the spacecraft's interior, the proprioceptive feedback from muscles and joints to construct a workable sense of orientation. But this is a constructed orientation, not a gravitationally given one. The astronaut's brain decides that down means the floor of the habitation module or the direction the displays are oriented, or whichever surface the crew treats as the floor by convention. This construction is workable and comfortable once established, but it is arbitrary in the physical sense. For a hypothetical spacecraft traveling perpendicular to the ecliptic, away from the planetary disk, the spacecraft's own gravitational field, created by the mass of the vehicle, would be the dominant source of up and down for the crew. This is a very weak gravitational field, far weaker than Earth's, but in the absence of any other gravitational guidance, even a tiny acceleration in one direction can define an up and down if the crew is stationary relative to the spacecraft. If the spacecraft uses constant acceleration for propulsion, the thrust creates an artificial gravity, and the floor becomes the surface facing opposite to the direction of thrust. This artificial gravity defines up and down for the crew very clearly, but the direction of this artificial gravity in the larger context of the solar system changes as the spacecraft maneuvers, making up in the artificial sense completely unrelated to any fixed direction in solar system geometry. The experience of long-duration spaceflight then involves a gradual decoupling of the personal experience of up and down, which remains strong and important in the practical management of life aboard a spacecraft, from any connection to a fixed direction in the solar system or the galaxy. Astronauts aboard the International Space Station experience a strong sense of up and down defined by the station's interior, but this sense is pointed in a direction that changes completely every 45 minutes as the station orbits Earth, rotating so that what was up relative to the station is now facing a completely different part of the sky. The ISS astronauts' experience is a preview of what deep space travel will involve: a persistent, practical, necessary experience of up and down defined locally by the spacecraft's structure and dynamics, entirely decoupled from any cosmic reference frame. There is one more dimension of this topic worth exploring carefully: the concept of the invariable plane, and what it reveals about the most accurate way to describe the solar system's orientation when you want to go beyond the ecliptic's Earth-centric bias. The ecliptic, as we have established, is defined by Earth's orbit. This makes it useful for Earth-based astronomy and for describing the positions of objects in the inner solar system. But it is inherently centered on one specific planet. Planetary scientists who want to describe the solar system's overall structure without privileging Earth's particular orbit use a different reference plane: the invariable plane. The invariable plane is defined as the plane perpendicular to the total angular momentum vector of the solar system. To compute it, you take the angular momentum of every body in the solar system, every planet, every moon, every asteroid, every comet, every grain of dust, add all those vectors together, and the result is the total angular momentum vector of the solar system. The invariable plane is perpendicular to this total vector. The invariable plane is invariable in the sense that it does not change over time or changes only extremely slowly. Individual planets' orbits precess and evolve over time, changing the ecliptic's orientation slightly over thousands and millions of years. But the total angular momentum of the solar system is conserved except for tiny effects from outside the solar system, so the invariable plane remains fixed even as individual orbital planes wobble. The invariable plane is dominated by the contributions of Jupiter and Saturn, the two most massive planets with the most angular momentum. It lies within about 0.5 to 1 degree of Jupiter's orbital plane, and it is tilted about 1.5 degrees from Earth's orbital plane, the ecliptic. For most purposes, these differences are small enough to be unimportant, but the invariable plane is the more physically fundamental reference. The direction perpendicular to the invariable plane, the true north of the solar system in the most rigorous sense, is also not pointed toward any bright star. It is in the constellation Coma Berenices, pointing toward a specific region of the sky that is somewhat north of the ecliptic but not dramatically so. If you wanted to say, "I'm going straight up out of the solar system," in the most physically rigorous sense, you would be going toward Coma Berenices, rising away from the ecliptic at roughly 1.5 degrees more steeply than you might naively compute from the ecliptic's perpendicular. This is not a direction that has any particular galactic significance. Coma Berenices is not toward the galactic center. It is not toward any notable structure in the galaxy. It is simply the direction perpendicular to the disk of material that happens to be orbiting this particular star. Let's synthesize everything we have explored tonight into a clear picture of what the solar system's geometry actually looks like, stripped of the familiar but misleading language of up and down. The solar system has a relatively flat inner disk, the region of the planets, defined by the conserved angular momentum of the protoplanetary disk that formed it. This disk extends from the Sun to roughly Neptune's orbit, with all 8 planets orbiting within a few degrees of the same reference plane. Beyond the planets, the Kuiper belt maintains some degree of flattening, with most objects within a few tens of degrees of the ecliptic. The scattered disk extends to higher inclinations. The Oort cloud is roughly spherical, with objects at all inclinations uniformly distributed. The heliosphere, the Sun's region of physical influence through the solar wind, extends in all directions, not just in the plane of the planets. The solar wind flows outward from the Sun's poles, just as it flows from the equatorial regions, reaching higher velocities at the poles and lower velocities near the current sheet in the equatorial region. The heliosphere is compressed in the direction of the solar system's motion through the interstellar medium, elongated in the trailing direction, but it is not absent above and below the ecliptic. The galactic plane, which defines a different kind of horizontal for the solar system, is tilted about 60 degrees to the ecliptic. The solar system bobs up and down through this galactic plane on a 30 to 35 million year cycle, affected by the galactic disk's tidal force in a way that has nothing to do with the ecliptic's perpendicular. The Sun moves through the galaxy at 230 kilometers per second in a direction roughly perpendicular to the north ecliptic pole, so the solar system's motion is sideways with respect to its own disk plane. The concept of up in this picture has no single unambiguous referent. It could mean away from Earth's surface, the most immediate and personal meaning, away from Earth's center in any direction. North of Earth's equatorial plane, celestial north. North of the ecliptic plane. North of the invariable plane. North of the galactic plane. Away from the Sun, radially perpendicular to the solar system's motion through the galaxy. Each of these is a legitimate and useful definition for specific purposes. None of them is more correct than the others in an absolute physical sense. The universe does not have a preferred up. What we have instead is a collection of reference frames, each revealing something about the structure of the solar system and our position within it. The night sky, which presents itself so naturally as an above, is the final illustration of tonight's theme worth sitting with carefully. When you look up at the night sky, you are looking outward from Earth's surface in the direction away from Earth's gravity. The stars you see are not above you in any cosmic sense. They are simply around you in the three-dimensional space that surrounds the solar system and the galaxy and everything we know. The sky is not a ceiling. It is the interior of a vastly larger space, and the directions you can look in it are arbitrary slices through a three-dimensional reality. Looking up at the Milky Way on a dark night, you are looking roughly toward the galactic plane, since the band of the Milky Way traces our galaxy's disk. Looking up at certain times of year means looking toward the galactic center, the densest part of the Milky Way's disk. Looking up at other times means looking toward the galactic anticenter, the direction away from the center, which is a less dense part of the disk. The word up contributes nothing to understanding these directions. The actual directions, toward or away from the galactic center, in or out of the galactic plane, are what matter. A visitor from another star, approaching the solar system, would organize the solar system's structure around the Sun, because the Sun is where the mass is. From a distant vantage point above the invariable plane, the planetary disk would appear flat, like a disk seen face-on, with the planets orbiting in nearly circular paths. There would be no up and down to the system as observed from outside. There would be an axis of symmetry, defined by the perpendicular to the disk plane, and there would be the disk plane itself, and everything else would be described relative to these structures. From that vantage point, the Earth would be a small dot orbiting within the disk at roughly 1 astronomical unit. The visitor would have no particular reason to use the direction of Earth's gravity as a reference. The visitor would probably use the system's invariable plane, or the Sun's equatorial plane, or the disk of the planets defined observationally as the reference frame. Earth's gravity defined up and down would be irrelevant from that perspective, just as we do not organize our descriptions of distant planetary systems around the gravitational orientation of their particular rocky inner planets. The dissolution of up is, in the end, a dissolution of the special status that the local experience of Earth's gravity has given to one particular direction in space. It is a humbling and a liberation. It turns the sky from a ceiling into a space, and it makes the question of where we are in the universe not a question of height, but a question of location in a three-dimensional structure that extends in all directions without privileging any of them. Let's close tonight's exploration with the practical wisdom that this dissolving of up offers to anyone who wants to genuinely understand the solar system and our place in it. When you read that a spacecraft is above the ecliptic, or that a comet comes from south of the ecliptic, or that the solar system's north pole points in a certain direction, you now understand what these descriptions mean and what they do not mean. They mean the object is on a particular side of a reference plane that astronomers find useful for organizing descriptions of the solar system. They do not mean the object is physically elevated above something or physically lower than something else. They do not describe a gravitational relationship. They are coordinate descriptions, as arbitrary as saying something is east of a given meridian line. When you see a diagram of the solar system with the planets orbiting in a flat plane, you understand that this flatness is real, but that the solar system extends in 3 dimensions around that plane, with objects at all inclinations, with the Oort cloud surrounding the system in every direction, with the heliosphere expanding spherically outward even above and below the planetary disk, with the galactic context imposing its own tilted reference frame from outside. When you look up at the night sky and feel the word up naturally arising, you can recognize it as the product of the gravity field beneath your feet, a local concept that served human beings beautifully for hundreds of thousands of years of life on Earth's surface. And that becomes gradually irrelevant as you move outward into the cosmos. The universe does not have an up. The galaxy does not have an up. The solar system has a reference plane, and above and below that plane, the same physics, the same forces, the same empty space extend in every direction with exactly equal validity. There is something freeing in this. The universe, in the direction of up, and in every other direction, extends farther than any concept of height can usefully describe. The stars you see overhead are not above you in any cosmic sense. They are beside you, around you, the nearest members of a community of 400 billion stars that extends in a disk tens of thousands of light years across, embedded in a universe that has no preferred orientation whatsoever. Up is what gravity makes. Gravity makes it different at every point, pointing always toward the nearest large mass, and large masses are distributed through the universe with no particular order that any word like up or down can capture. The universe is sideways and inside out, and every direction at once, and the sky above you is not a ceiling over a world, but a window into a space that extends in every direction you can point without end. This is After Dark Space. Wherever you are, I hope the exploration goes somewhere useful. Let's spend more time with the physics of what actually keeps the solar system flat, because the explanation involves some of the most beautiful mechanics in all of classical physics, and understanding it properly reveals why the flat disk is not a permanent feature of the solar system, but a temporary artifact of its particular moment in time. Angular momentum is the central concept. An object moving in a circle has angular momentum, which is roughly the product of its mass, its speed, and the radius of its circular path. Angular momentum is conserved unless an external force acts to change it, a consequence of Noether's theorem and the rotational symmetry of the laws of physics. In a closed system, the total angular momentum stays constant. The protoplanetary disk that formed the solar system was a rotating cloud of gas and dust that had a net angular momentum from small initial perturbations in the original gas cloud. As this cloud collapsed under gravity, the collapse was free in all directions, but angular momentum conservation prevented the material from collapsing fully in the direction perpendicular to the rotation axis. Material could collapse inward toward the rotation axis relatively easily because that motion didn't require changing the angular momentum much. But material couldn't easily move above or below the disk's plane because doing so would have required changing the orientation of the angular momentum, which is resisted. This is why the cloud flattened. Gravity pulled material inward, and angular momentum conservation resisted the collapse only in the plane perpendicular to the rotation axis, causing the cloud to flatten into a disk around the Sun rather than collapsing into a tight sphere. Once the disk formed and the planets started to grow within it, those planets inherited the disk's flat, coplanar arrangement. But the disk itself was not static. Over time, the gas in the disk was expelled by solar winds and radiation pressure from the young Sun. What remained were the solid bodies, the planets, the asteroids, the leftover planetesimals. Without the gas disk's damping influence, the gravitational interactions between planets began to operate freely. These interactions are not perfectly stabilizing. Planets gravitationally perturb each other's orbits over time, causing small oscillations in inclination and eccentricity. The inner planets, including Earth, undergo coupled oscillations in their orbital inclinations with periods of hundreds of thousands to millions of years, driven by their mutual gravitational interactions. These inclination oscillations mean that the ecliptic, defined by Earth's orbit, is not fixed but slowly wobbling. The ecliptic is the least stable of all the reference planes we have discussed. Earth's orbital inclination relative to the invariable plane oscillates between about 1 and 3 degrees with a period of tens of thousands of years. The ecliptic is a moving target. The invariable plane, by contrast, is stable because it is defined by the conserved total angular momentum. It does not oscillate. It is the closest thing the solar system has to a permanent, physically motivated reference plane. The flatness of the solar system's inner disk is maintained in the present epoch, not by any ongoing force flattening it further, but by the inertia of the angular momentum already present. The planets were placed in near coplanar orbits by the disk, and they have stayed there because the gravitational perturbations between them, while they cause oscillations, do not systematically tilt all the orbits away from the disk plane. The system oscillates around a roughly flat configuration because the total angular momentum constrains it to do so. Over very long timescales, the flatness of the solar system's inner disk could change. If a large, massive body with a high inclination orbit were added to the solar system, its angular momentum would change the total angular momentum vector, and the invariable plane would tilt. The existing planet's orbits would be perturbed toward the new invariable plane, gradually tilting the disk to accommodate the angular momentum of the intruder. This is thought to be one of the mechanisms by which exoplanetary systems develop misaligned planetary orbits. The rotation of the Sun itself and its relationship to the ecliptic contains a small but significant mystery that we touched on briefly and that deserves more thorough examination, because it connects the question of up in the solar system to fundamental questions about the Sun's history and the history of angular momentum in the solar system's formation. The Sun rotates with its equatorial plane tilted about 7.25 degrees relative to the ecliptic. This is the solar obliquity, and it has been puzzling solar physicists since it was first accurately measured. In the simplest model of solar system formation, the Sun would have formed from the same collapsing cloud as the disk, and its rotation axis would align with the angular momentum axis of the disk. The Sun's equatorial plane would then be very nearly the same as the ecliptic. The fact that it is tilted by 7.25 degrees tells us that something happened to either rotate the Sun slightly relative to the disk or to tilt the disk slightly relative to the Sun. The leading candidates for this tilt have each interesting implications. One possibility involves the transport of angular momentum between the Sun and the disk during the formation epoch. As the young Sun accreted material from the disk, and as the Sun shed mass and angular momentum in the T Tauri wind, a phase of intense stellar wind early in the Sun's life, the exchange of angular momentum between the Sun and disk could have resulted in a slight misalignment between the Sun's spin axis and the disk's angular momentum axis. Another possibility involves a close encounter with another star in the young Sun's birth cluster, which could have gravitationally tilted the outer disk relative to the Sun's equatorial plane. The inner disk, more tightly coupled to the Sun, might have been less affected than the outer disk, creating a small but persistent misalignment. A third and more dramatic proposal involves the gravitational influence of an as-yet undetected planet in the far outer solar system, the hypothetical Planet 9, which has been invoked to explain several anomalies in the outer solar system. A massive planet on a highly inclined orbit at great distance could, over billions of years, have torqued the inner solar system's angular momentum vector slightly away from the Sun's equatorial plane, producing the observed 7.25-degree tilt. This prediction of the Planet 9 hypothesis is testable in principle, and it is one of the reasons some planetary scientists take the Planet 9 hypothesis seriously, despite the absence of direct detection. The solar obliquity, the 7.25-degree tilt between the Sun's rotation and the ecliptic, is thus not just a bookkeeping issue for coordinate systems. It is a forensic clue about the history of the solar system's earliest dynamics. Whatever caused this tilt left an enduring mark on the relationship between the Sun's spin and the plane in which the planets orbit, a mark that will remain long after all the original gas and dust of the formation epoch have been swept away. The story of how planetary inclinations change over time, called secular orbital evolution, is one of the most beautiful and most counterintuitive results of celestial mechanics, and it deepens the understanding of why up and down in the solar system are concepts that shift rather than being fixed. Isaac Newton's law of gravitation describes the force between any two bodies at any instant of time. But planetary systems are not two-body systems. They have many bodies all pulling on each other simultaneously, and the long-term behavior of a many-body gravitational system cannot be solved exactly, only approximated. The first systematic approach to understanding the long-term behavior of planetary orbits was developed by Lagrange, Laplace, and later by Gauss, Poincaré, and many others, in a branch of celestial mechanics called secular theory. In secular theory, you average the gravitational interactions between planets over their orbital periods, replacing the actual time-varying forces with their time-averaged equivalents. This smoothing reveals the slow, long-period oscillations in orbital elements that emerge from the cumulative effects of gravitational interactions over millions to billions of years. For the inclinations of the inner planets, secular theory predicts that all four inner planets undergo coupled oscillations. Earth's orbital inclination to the invariable plane oscillates with several superimposed periods, the dominant period being about 70,000 years for the main inclination mode, with additional periods of hundreds of thousands of years. Mars has similar coupled oscillations. Venus and Mercury are also coupled into the secular inclination oscillations. The key insight is that the planet's inclination oscillations are not independent. They are locked together by the secular gravitational coupling between them. As Earth's inclination increases, Mercury's and Venus's inclinations respond. When Earth's inclination is at a maximum, the specific values of the other planets' inclinations are determined by the secular mode in which the system is oscillating. For the outer planets, Jupiter's and Saturn's secular inclination modes are coupled together, as are Uranus's and Neptune's. The timescales are much longer for the outer planets due to their slower orbital periods. but the physics is similar. What this means for the concept of up in the solar system is that the angle of the ecliptic relative to the invariable plane is not fixed. Earth's orbital inclination to the invariable plane changes over tens of thousands to hundreds of thousands of years. The ecliptic itself wobbles. The direction that we define as north of the ecliptic slowly changes because the ecliptic's orientation changes because Earth's orbital inclination oscillates due to secular coupling with the other planets. On a human timescale of years or centuries, this wobble is imperceptible. But on the timescale of tens of thousands of years, the ecliptic's orientation relative to the invariable plane changes measurably. The up of the ecliptic coordinate system in 100,000 years will be pointing in a slightly different direction than it does today. This is the final layer of the dissolution of up in the solar system. Even the reference planes that we use to define up and down are themselves slowly moving, oscillating, precessing, and evolving under the same gravitational forces that shape all the other dynamics of the solar system. Planets around other stars exhibit remarkable diversity in their axial tilts, which provides a comparative perspective on Earth's own obliquity and on the question of what counts as up for a planet in a solar system. Earth's axial tilt of 23.4 degrees, which creates the seasons and which defines the angle between the equatorial plane and the ecliptic, is often treated as a somewhat typical value. But the range of axial tilts among the solar system's planets is actually quite large. Uranus has an axial tilt of 98 degrees, meaning it rotates nearly on its side, with its poles alternately pointed toward and away from the Sun as it orbits. Venus has an axial tilt of 177 degrees, which is essentially upside down. Venus rotates in the opposite direction from most planets, and the retrograde rotation means the Sun rises in the west and sets in the east on Venus. These extreme axial tilts are thought to result from large impacts during the formation of the solar system. Uranus in particular is believed to have been struck by an Earth-sized body during the period of heavy bombardment, knocking its rotation axis sideways. Venus's retrograde rotation may also result from a large impact, or alternatively, from tidal interactions with the Sun and its thick atmosphere over billions of years. For a planet with Uranus's axial tilt, the question of up in the sense of perpendicular to the orbital plane is almost entirely decoupled from the local definition of up on the planet's surface. For most of Uranus's 84-year orbital period, the planet's poles are not significantly tilted toward or away from the Sun, and the planet's local gravity defines up as pointing away from the planet's center, just as on Earth. But the orientation of down relative to the ecliptic changes dramatically depending on where in Uranus's orbit you are standing. For exoplanets, we know even less about axial tilts because they are extremely difficult to measure for distant planets. But theoretical considerations suggest that planets' axial tilts are set largely by the history of impacts during formation, which is a random process, and by subsequent tidal evolution, which for close-in planets can drive the axial tilt towards zero or toward large values depending on the specifics of the planet-star interaction. The diversity of axial tilts among exoplanets is probably large. This diversity of axial tilts further underscores the arbitrariness of up as a cosmic concept. Each planet has its own local up, defined by its own gravity field. Each planet's local up points in a different direction relative to the ecliptic, the galactic plane, and every other reference frame. There is no consistent up across even the planets of our own solar system, let alone across the planets of the galaxy. There is one more physical phenomenon worth exploring in the context of vertical direction in the solar system, and it involves the solar system's rotation as a whole and the direction that rotation implies. If you could hover far above the solar system and watch the planet's orbit, you would see them all moving counterclockwise when viewed from the north ecliptic pole, the north that the conventional coordinate system defines. This is not an accident, but a consequence of the direction of the original protoplanetary disk's rotation. The disk rotated counterclockwise as seen from this direction, and the planets inherited this rotation. The Sun itself also rotates counterclockwise as seen from the north ecliptic pole, though, as we discussed, its equatorial plane is tilted 7.25 degrees from the ecliptic. The Sun's north pole points roughly in the same direction as the ecliptic's north pole, just with a 7.25 degree offset. This common direction of rotation, counterclockwise from the north, is sometimes used to define north in the solar system. North is the direction from which the orbital motion appears counterclockwise. This is the right-hand rule applied to the solar system. If you curl the fingers of your right hand in the direction of orbital motion, your thumb points north. But this definition is circular in a subtle way. We define north as the direction from which motion is counterclockwise, and then we observe that from this direction, the motion is indeed counterclockwise. The definition contains the conclusion. We could equally well define south as the direction from which motion appears counterclockwise, and from that direction, the motion would appear counterclockwise, because we defined our south to be where we're looking from. The counterclockwise motion defines north only if we have already decided that counterclockwise motion defines north. The actual physical content of this observation is simply that the solar system has a definite sense of rotation. It rotates one way rather than the other. This is a real physical fact, but the assignment of that rotation as counterclockwise from the north or as clockwise from the south is a convention, not a fact about the universe. In the absence of a biological preference for one direction of rotation, humans do have a slight statistical preference for counterclockwise in certain tasks, but this is irrelevant here. There is no physical reason to call the direction from which the solar system's rotation appears counterclockwise north rather than south. We call it north because terrestrial north conventions and astronomical conventions have been unified to be consistent with each other, and that unification dates from the earliest days of systematic astronomy, when the decision was made to align celestial north with terrestrial north. This historical contingency is the deepest root of the solar system's north. It is not a consequence of any asymmetry in the laws of physics. It is not a consequence of any particular feature of the solar system's formation. It is a consequence of a convention established by astronomers who lived in the northern hemisphere of Earth and who chose to align their coordinate systems with the direction their compasses pointed. The history of coordinate systems in astronomy is worth tracing briefly because it illustrates how the concepts we use to describe up in the solar system are deeply embedded in historical and cultural choices that have nothing to do with the physics of the solar system. The earliest astronomical coordinate systems were essentially projections of terrestrial geography onto the celestial sphere. The celestial equator, still used in the equatorial coordinate system for describing star positions, is simply Earth's equatorial plane projected outward to the sky. The celestial poles, north and south, are projections of Earth's rotation axis. Right ascension, one of the two coordinates in the equatorial system, is measured from the vernal equinox, a point in the sky defined by where the Sun crosses the celestial equator moving northward in spring. This is not a special point in space. It is a special point in the annual cycle of the Sun as seen from Earth. These coordinate choices were made for practical reasons. They allowed astronomers to connect observations of the sky to the rhythms of Earth's rotation and orbit, which were the basis of all timekeeping before atomic clocks. The celestial equator and equatorial poles moved predictably as Earth rotated, which made them useful reference points for predicting where stars would be at any given time of night. The vernal equinox was tied to the calendar, which was of obvious practical importance. The ecliptic coordinate system was developed for a different practical purpose: describing the positions of the Sun, Moon, and planets, which all move close to the ecliptic. Using the ecliptic as the reference plane makes the paths of the planets nearly straight lines in the coordinate system rather than complex curves. This simplification was valuable for ancient astronomers who wanted to predict planetary positions. Both coordinate systems were invented before there was any real understanding of what the solar system was. The ecliptic was the path of the Sun in the sky, not understood as Earth's orbital plane. The celestial equator was the projection of Earth's equator, not understood as a consequence of Earth's rotation. The coordinate systems preceded the understanding of the physical reality they were describing. By the time modern physics had revealed the actual structure of the solar system, these traditional coordinate systems were so deeply embedded in astronomical practice, in catalogues, in reference tables, in the software of telescopes and planetariums that they remained even though better motivated coordinate systems could have been designed from scratch. The ecliptic coordinate system and the equatorial coordinate system are both artifacts of the history of observational astronomy, optimized for ease of calculation in the pre-computer era and maintained by inertia even after their physical motivation had been superseded. This is not a criticism. The systems work. They are internally consistent. They can be converted to each other and to any other coordinate system by well-defined transformations. But they do represent a specific historical choice to anchor the description of the solar system to the features of one particular planet, Earth, rather than to the most physically fundamental properties of the solar system as a whole. The invariable plane would be a more physically motivated choice, but it is rarely used outside of specialized planetary science contexts because it is not tied to any easily observed phenomenon. The point is that up in the solar system, defined as north of the ecliptic, is not only physically arbitrary but historically contingent. It is the way it is because of where early astronomers lived and what they were trying to accomplish, not because the universe had anything in particular to say about the matter. Let's step even further back and consider the question of direction in space at the scale of the galaxy, because the complete dissolution of up requires following the logic all the way to its conclusion, and the galactic scale is where that conclusion is most clearly visible. The Milky Way is a barred spiral galaxy, a flat disk roughly 100,000 light-years across and perhaps 1,000 light-years thick in our neighborhood of the disk, though it thickens toward the center and becomes very thin in the outer regions. The disk is surrounded by a roughly spherical halo of older stars, dark matter, and globular clusters that extends to several 100,000 light-years in every direction. The Milky Way has a rotation axis, just as the solar system does. Viewed from one galactic pole, the disk's spiral arms appear to rotate counterclockwise. Astronomers call the direction from which this rotation appears counterclockwise the North Galactic Pole, and it is in the constellation Coma Berenices, roughly perpendicular to the Milky Way's disk as seen from the solar system's perspective. The galactic coordinate system, centered on the center of the Milky Way with the galactic plane as the reference, is often used for describing large-scale structures in the galaxy and beyond. Galactic latitude measures how far above or below the galactic plane something is, with the galactic North Pole being defined by the galactic North Pole direction in the same way that ecliptic latitude is defined by the ecliptic North Pole. But is the galactic plane's North Pole in any physical sense the up of the universe? No. The Milky Way is just one of roughly 2 trillion galaxies in the observable universe, and each one has its own plane of rotation and its own poles. There is no preferred reference plane for the universe as a whole. The universe, as far as we can tell, is isotropic and homogeneous on the largest scales. It looks the same in all directions, and the same laws of physics apply everywhere. There is no preferred direction in the universe that could serve as a cosmic up. The universe has no top, no bottom, no center, no edge in any directional sense. When physicists talk about the early universe in terms of the Big Bang, they sometimes say the universe began from a point and expanded outward, which sounds like there should be a center and a direction of expansion. But this description is misleading. The universe did not expand outward from a point in space. Space itself expanded. The expansion is uniform. Every point in the universe recedes from every other point in the universe, not because of motion through space, but because the space between them is growing. There is no center of the expansion, no direction of the expansion, no outward relative to which a direction can be defined. The most fundamental answer to which way is up in the solar system is that the universe itself has no answer to this question. The universe is directionally neutral. The solar system has a reference plane, Earth has a gravity field, and humans have an inner ear that detects which way is down. But none of these are cosmic facts. They are local facts, true in specific places under specific physical conditions and meaningful only in those contexts. There is a richly human dimension to the question of direction in space that is worth closing with, because the exploration of these ideas is not just about the physics, but about what it means for human beings to inhabit a universe without absolute orientation. The entire history of human navigation on Earth, from the first sailors following coastlines to the invention of the compass to the development of global positioning systems, is a history of finding references to navigate by. Polaris in the night sky, the position of the sun at noon, the direction of prevailing winds, the bearing of a distant mountain. All of these are local references, true in a specific place on Earth, useful for navigation in that context. The history of navigation beyond Earth, from the Apollo lunar missions to the trajectories of interplanetary probes, required learning to navigate without the Earth-based references that had served for millennia. Spacecraft navigators do not use compass points. They use star trackers, gyroscopes, and communication links with Earth-based antennas to determine orientation and position. The reference systems they use are arbitrary coordinate systems, chosen for mathematical convenience that happen not to align with any feature of the physical landscape. This transition from embedded environment-dependent navigation to abstract, coordinate-dependent navigation is a useful metaphor for the broader transition in our understanding of direction. The concept of up is a form of embedded navigation rooted in the specific physical environment of Earth's surface. It is a profoundly useful concept in that environment, just as a compass bearing is a profoundly useful concept for a sailor. But it is not portable to the cosmos in the way that a compass is not useful beyond Earth's magnetic influence. What replaces up in the cosmos is not a better version of the same concept, but a different kind of relationship to space entirely. The question becomes not where is up, but where are we and what are the reference structures around us? These are questions about structure, not about height. They require knowing the orientation of the galactic disk, the position of the nearest large mass concentrations, the direction of the sun or the galactic center, the local magnetic field, the cosmic microwave background dipole that reveals the solar system's motion through the universe. None of these is up. All of them are directions, with physical meaning in specific contexts, and none of them is more fundamental than the others in a cosmic sense. Human beings standing on Earth's surface will continue to experience up and down with the full immediacy and conviction of direct physical experience. Gravity is a powerful teacher, and Earth's gravity has been teaching every human being who has ever lived the same lesson about direction. Down is toward the ground, up is away from it. But the sky above, which looks so clearly like an up from the surface, is not a ceiling. It is a window into a three-dimensional universe that extends in every direction, including down through the planet and out the other side, just as it extends above, and in which the concepts of up and down dissolve into the richer, more neutral, more accurate language of location, orientation, and structure. The dissolution of up is one of the small cognitive revolutions that comes with really understanding where we are. It does not diminish the immediate experience of living on Earth's surface. It adds to it. It makes the sky more than a ceiling. It makes the ground beneath your feet more than a floor. It makes the entire planet a small, round, gravity-bound object in a universe that has no preferred orientation and no vertical axis, surrounded by structures and forces and phenomena in every direction equally, including the direction we have always, with such certainty, called up. The night is quiet, and the exploration has gone as far as it needs to go tonight. What lies above the solar system? Exactly what lies below it? Exactly what lies to the side of it? The heliosphere extending outward. The interstellar medium beyond the heliopause. The spiral arm of the Milky Way within which the solar system is embedded. The galactic disk extending in all directions in the plane. The halo of the galaxy above and below the disk. And beyond that, the universe. Isotropic, directionless, the same in every direction, as far as observation can reach and almost certainly beyond. The solar system is not a vertical structure. It is a flat disk embedded in three-dimensional space, with the flat part of the structure extending in one plane and the rest of the solar system, the Oort Cloud, the heliosphere, the extended gravitational influence of the Sun surrounding it in every direction. Up is the direction away from the nearest large mass. On Earth, that direction is vertical. In the solar system, that direction is radial, pointing away from the Sun in every direction simultaneously. In the galaxy, down is vaguely toward the galactic center, though the galactic gravity is too diffuse to create a strong sense of direction for an individual observer. In the universe, there is no down at all. This is after dark space. The answers to the simplest sounding questions are often the most revealing about where we actually are. There is a specific and fascinating observational program that makes the question of direction in the solar system concrete in a way that calculations alone cannot. The attempt to measure the solar system's motion through the universe using the cosmic microwave background. The cosmic microwave background, the faint afterglow of the Big Bang that permeates the entire universe, is remarkably uniform in every direction. It was produced when the universe was about 380,000 years old, when the hot plasma that filled the early universe cooled enough for electrons and protons to combine into neutral hydrogen, releasing the photons that had been trapped in the plasma. These photons have been traveling freely ever since, redshifted by the universe's expansion from their original thermal emission at about 3000 Kelvin to their current temperature of about 2.73 Kelvin. The cosmic microwave background is uniform to about 1 part in 100,000, meaning that in any two directions in the sky, the temperature of the background differs by only about 0.00001 degrees. This uniformity is one of the great confirmations of the Big Bang model and of the cosmological principle, which holds that the universe is isotropic and homogeneous on large scales. But there is one large-scale variation in the cosmic microwave background temperature that is not due to the structure of the early universe. It is due to the motion of the solar system. The solar system is moving through space, and this motion causes the cosmic microwave background to appear slightly hotter in the direction we are moving toward and slightly cooler in the direction we are moving away from. This effect, called the CMB dipole, is analogous to the Doppler shift of sound. When you move toward a sound source, the sound waves are compressed and the pitch is higher. When you move away, the waves are stretched and the pitch is lower. By measuring the amplitude and direction of the CMB dipole, astronomers can determine both the speed and direction of the solar system's motion relative to the cosmic microwave background. This measurement reveals that the solar system is moving at about 370 kilometers per second in the direction of the constellation Leo, or more precisely in the direction of galactic coordinates that correspond to roughly the Leo constellation. This direction of solar system motion toward Leo at 370 kilometers per second is a real physical fact about the solar system's orientation in the universe. It defines a direction that has genuine physical content, the direction of the solar system's motion relative to the cosmic rest frame. If any direction deserves to be called forward for the solar system in the universe, this is it. But notice what this direction is not. It is not up. It is not perpendicular to the ecliptic. It is not aligned with the North Galactic Pole. It is a direction in the plane of the sky that cuts across all the conventional reference planes at a distinctive angle. The solar system's motion through the cosmic background is pointing roughly toward Leo, which is in the northern sky from Earth's perspective, but is not at any ecliptic or galactic pole. This direction encodes the cumulative effect of the solar system's motion within the Milky Way, the Milky Way's motion within the local group, and the local group's motion toward the Great Attractor, a concentration of mass in the direction of Centaurus that is pulling the local group and many surrounding galaxy clusters gravitationally. The 370 kilometers per second motion revealed by the CMB dipole is the combined velocity arising from all these gravitational influences. The direction toward Leo, toward which the solar system is speeding at 370 kilometers per second, is the closest thing the universe gives us to a definition of forward for our position in the cosmos. It has nothing to do with up. The specific ways that spacecraft missions have been affected by the solar system's geometry and by the question of direction within it provide concrete examples that ground the abstract physics in the history of exploration. The New Horizons mission to Pluto illustrates the practical importance of the ecliptic geometry in mission planning. Pluto's orbit is tilted about 17 degrees to the ecliptic, meaning that when New Horizons encountered Pluto in July 2015, the spacecraft was not in the ecliptic plane. It was about 17 degrees south of the ecliptic, having been directed by mission planners toward Pluto's position at the time of encounter. This meant that the communication geometry between New Horizons and Earth-based antennas was affected by the spacecraft's out-of-ecliptic position. The Deep Space Network antennas, located at 3 sites around the world to provide continuous coverage as Earth rotates, are optimized for communication with spacecraft in roughly the ecliptic plane where most planetary targets are found. A spacecraft significantly out of the ecliptic, as New Horizons was during and after the Pluto encounter, requires somewhat different communication scheduling as Earth's rotation cycles through the geometries that allow each antenna site to track the spacecraft. The Ulysses mission, as discussed, was specifically designed to reach high solar latitudes, requiring it to travel significantly above and below the ecliptic. The trajectory design for Ulysses was extraordinary. Launched in 1990, the spacecraft first traveled outward to Jupiter, then used Jupiter's gravity to swing into a highly inclined orbit over the solar poles. This gravity assist from Jupiter was the only practical way to achieve the high inclination orbit within the mission's mass and energy budget, because getting a spacecraft significantly out of the ecliptic plane under its own propulsion requires enormous amounts of energy. The energy requirement to go up out of the ecliptic to leave the plane of the planets is much larger than the energy required to travel from one planet to another within the ecliptic. To travel from Earth to Mars within the ecliptic plane, a spacecraft needs to change its velocity by a few kilometers per second. To change a spacecraft's orbital inclination significantly, moving it above or below the ecliptic requires velocity changes comparable to or larger than the orbital velocity itself, which is tens of kilometers per second. Going up out of the solar system's disk is energetically much more expensive than going along it. This energy asymmetry has a physical explanation rooted in the flat disk structure. The planets formed in a disk because angular momentum conservation flattened the original cloud. All the material in the disk has angular momentum directed perpendicular to the disk, so all orbits in the disk are aligned with this angular momentum. To leave the disk, a spacecraft must add or remove angular momentum from its orbit, changing the direction of its orbital angular momentum vector, which is the most energetically expensive type of orbital maneuver. This is why it was necessary to use Jupiter's gravity to redirect Ulysses into a polar orbit. A rocket powerful enough to do this directly would have been impractically large. The practical consequence for space exploration is that the solar system is most accessible in its ecliptic plane, where the planets are, and least accessible above and below the ecliptic, where there is nothing nearby to visit. The flat disk is not just a description of where things are. It is a constraint on where exploration can practically go, because the energy cost of going up or down out of the disk is prohibitive with current and near-future propulsion technology. The question of whether other solar systems have ups and downs that are comparable to ours, and what we would mean by that, connects the specific physics of our solar system to the more general question of planetary system geometry across the galaxy. Multi-planet exoplanetary systems that have been discovered by the Kepler and TESS missions show a range of mutual inclination structures. In many systems, particularly the closely packed systems of super-Earths that Kepler discovered in large numbers, the planets are all nearly coplanar, orbiting within a few degrees of the same plane. These systems, in their geometry, are superficially similar to our solar system, a flat disk of planets with a vertical direction perpendicular to the disk that is physically vacant. But the orientation of these systems' disks relative to our sky is entirely random. Some of these systems have their disk planes oriented edge-on, as seen from Earth, which is why the transit method detects them. The planets cross in front of the star from our line of sight. Others have their disk planes oriented at various angles, and we can only detect their planets through other methods like radial velocity. The up direction for each of these systems, the direction perpendicular to its planetary disk, points in a different random direction for each system, uncorrelated with any external reference. The systems that show misaligned planets, where inner and outer planets orbit in significantly different planes, are of particular interest for understanding how planetary systems evolve. A system with a giant planet in a highly inclined orbit can torque the orbital planes of other planets over billions of years, creating a system where up, as defined by one planet's orbital plane, is significantly different from up, as defined by another planet's orbital plane in the same system. Hot Jupiters, the giant planets orbiting very close to their host stars with orbital periods of a few days, are often misaligned with the host star's equatorial plane. The angle between a hot Jupiter's orbit and the star's equatorial plane can range from nearly 0 to nearly 180 degrees, with many hot Jupiters orbiting at substantial obliquities or even in retrograde orbits. For these systems, there is no consistent up. The star's rotation, the planet's orbit, and any other planet's orbits all point in different directions. The diversity of exoplanetary systems' orientational structures underscores the point that the flat, coplanar, prograde architecture of our solar system, while not rare, is not universal. The concept of the ecliptic as a reference plane is specific to our solar system, and even within our solar system, it is specific to Earth's orbital plane. Exoplanets have their own ecliptics, their own invariable planes, their own reference systems, all of them pointing in different directions relative to any external reference. The universe does not provide a universal reference plane. Each planetary system has its own, defined by its own dynamical history and its own angular momentum structure, and these are all independent of each other. Let's revisit one of the most fundamental concepts in physics and see how it relates to the question of direction in the solar system: the concept of symmetry. Physicists have a precise way of talking about the absence of a preferred direction. They say the universe is rotationally symmetric. Rotational symmetry means that if you rotate the universe by any angle about any axis, the laws of physics look the same. There is no experiment you can do that will tell you whether you are in a universe that has been rotated relative to the original by, say, 37 degrees about some axis. This rotational symmetry of the laws of physics is not just an abstract statement. It has a deep consequence, derived by the mathematician Emmy Noether in her famous theorem. Every continuous symmetry of the laws of physics corresponds to a conserved quantity. The rotational symmetry of the laws of physics corresponds to the conservation of angular momentum. Because the laws of physics are the same regardless of orientation, angular momentum is conserved in any isolated system. The connection to the solar system's flat disk is direct. The disk formed because angular momentum is conserved. The original cloud's angular momentum determined the disk's orientation and prevented the cloud from collapsing in all directions equally. The disk's current orientation and the current angular momenta of all the planets are consequences of the angular momentum conserved from the initial conditions of the solar system's formation. But the rotational symmetry of the laws of physics also means that there is no preferred direction built into the universe. The universe doesn't care which way is up. Any particular direction, including the direction perpendicular to the ecliptic, is just as valid or invalid as any other direction from the universe's perspective. The universe's rotational symmetry is the deep reason why the concept of up in the solar system, or in the galaxy, or in the universe is not physically fundamental. The conservation of angular momentum explains why the disk is flat and why the disk has the orientation it does. But the rotational symmetry from which angular momentum conservation follows tells us that the disk could have been flat in any direction, and no physical law would have prevented it from pointing in any other direction. The specific direction the solar system's disk is pointing is a consequence of the initial conditions of the molecular cloud from which it formed, not a consequence of any physical law preferring that direction. This is the most fundamental answer to the question of up in the solar system. The universe is rotationally symmetric. It has no preferred direction. The solar system has an orientation, determined by historical initial conditions, but this orientation is not privileged by any law of physics. Up in the solar system is a label we apply to one of the two perpendicular directions to the disk, and the choice of which direction to call up rather than down is a convention, not a fact. Before the final close, it's worth spending a moment with the practical implications for our self-understanding as inhabitants of this solar system. We live on a planet in a disk. The disk is flat because of angular momentum. The disk's north direction is conventional. The disk's orientation in the galaxy is random in the sense that no cosmic preference determined it. Our experience of up and down on Earth's surface is a consequence of the planet's gravity, which points radially inward. All of these facts together produce a picture of the human experience of direction as something locally generated, not cosmically given. We experience up and down because Earth's gravity is strong enough to organize our experience of space. We experience the sky as above because we live on Earth's surface rather than floating in space. We experience the stars as being out there rather than up there, only when we force ourselves to think carefully about what the geometry actually is. The night sky you have looked up at, perhaps all your life, will look different after tonight's exploration. The stars are not above the Earth. They are to the side of it, around it, in every direction, including the one that your planet's gravity calls down. The Milky Way band, stretching across a dark night sky, is not overhead in any cosmic sense. It is a cross-section of the galactic disk, and whether you are standing in the northern hemisphere or the southern hemisphere, whether it is overhead or near the horizon, the physical structure you are looking at is the same. A flat disk of stars extending 100,000 light-years, of which the solar system is an ordinary member roughly halfway from center to edge. The planets, when you spot them in the night sky, are not up there in any meaningful sense. They are to the side of Earth in the solar system disk, sometimes visible in the sky you happen to be looking at from your current location on Earth's rotating surface, sometimes below the horizon and visible from the other side of the planet. The concept of their being above you is an artifact of your position on Earth's surface, not a fact about their position in the solar system. The dissolution of up is not a loss, it is a gain. It opens the sky from a ceiling into a surrounding. It makes the Earth not the bottom of the universe, but a point in a three-dimensional space that extends in every direction. It makes the solar system not a vertical hierarchy, with the sun at the top and the outer planets below, but a flat disk embedded in space, surrounded in every direction by more space and defined by the specific angular momentum that happened to characterize the gas cloud from which it formed. We are not at the bottom of the universe. We are not at the top. We are here on this particular rotating planet, orbiting this particular star in this particular orientation that has no cosmic significance. And the sky around us, in every direction, extends farther than any concept of height can usefully describe. Good night.